Time and space are like a fabric, like rubber, like a trampoline net. Turn this trampoline net into a pretzel and allow yourself to go backwards in time.
Stephen Hawking, in his latest book, says God, bah humbug. He can prove the non-existence of God.
As physics progresses, our barriers are broken. However, at this stage, space and time, the most intuitive and fundamental concepts, may need to be abandoned in order for us to make further advancements. Recently captured images by NASA's James Webb Space Telescope reveal something in deep space that defies explanation, rewriting cosmic history and challenging our previous beliefs. What did this powerful telescope discover about the existence of time? Did the James Webb Telescope truly prove that time does not exist? Join us as we delve into the astonishing revelation made by the James Webb Telescope, shaking the entire space industry by questioning the existence of time. The James Webb Space Telescope addresses many of the fundamental questions that have captivated astronomers for the past 50 years. It stands as one of the most ambitious and costly engineering projects ever undertaken, with a price tag of $10 billion. Already, our understanding of distant planets and deep time is undergoing a revolution thanks to the James Webb Space Telescope. This remarkable instrument collects and focuses the faint light emitted by the farthest galaxies in the sky, allowing us to observe them as they appeared in the distant past when the universe was young. To achieve this, a mirror of unprecedented size and smoothness is required. However, a mirror alone is not sufficient to unlock the secrets of the early universe. We need to comprehend the nature of the first, possibly enormous, stars, understand the invisible matter that influenced their formation, explore the roles of magnetism and turbulence, and investigate the growth of supermassive black holes at the centers of galaxies. The James Webb Space Telescope, unlike anything before it, has been sent into orbit to tackle these profound questions. It delves into the earliest stars in the universe, searches for evidence of extraterrestrial life, and even challenges conventional wisdom. The Hubble Space Telescope has already revealed the existence of stars, galaxies, and supermassive black holes much earlier in cosmic history than previously believed, as well as their subsequent transformations. We now recognize that dark matter and dark energy shape the cosmos. Thanks to instruments like the Kepler telescope, we have also discovered a diverse range of exoplanets, including billions that may be potentially habitable within our own Milky Way galaxy. These discoveries have sparked numerous inquiries that the James Webb Space Telescope is now attempting to answer. Astronomers have labeled 6 enormous, ancient galaxies detected by the James Webb Satellite Telescope as universe breakers due to their potential to challenge established cosmological theories. These galaxies are much larger than what was deemed possible for galaxies in the early stages after the Big Bang. They date back to a time when the universe was only 3% of its current age. If confirmed, these discoveries would cast doubt on our understanding of how the first galaxies formed. Joel Leisure, an assistant professor of astronomy and astrophysics at Penn State University and a research co-author, expressed astonishment at the unexpectedly massive nature of these galaxies, given their early formation. The observations relied on the initial dataset provided by the Webb Space Telescope, equipped with infrared sensors capable of capturing even the faintest light from distant stars and galaxies. Dr. Erica Nelson, a co-author from the University of Colorado Boulder, identified a group of exceptionally bright and unusually red fuzzy dots while examining the photographs. In astronomy, the redness of objects serves as an indication of their age, as the light gets stretched or redshifted as it traverses the expanding universe. These galaxies appeared to be approximately 13.5 billion years old, placing them between 500 million and 700 million years after the Big Bang. These are not the oldest galaxies observed by the James Webb Telescope, which commenced operations in December 2021. Last year, scientists discovered galaxies that were approximately 350 million years old, although significantly smaller. However, calculations reveal that the recently observed galaxies have a mass equivalent to tens to hundreds of billions of stars like our Sun, putting them on par with the size of the Milky Way. Nelson exclaimed, "It's incredible. It shouldn't have been possible for these galaxies to form." Scientists now face the challenge of re-evaluating fundamental cosmological principles or revising their understanding of the early formation of galaxies from dust and stars in order to explain the appearance of such immense galaxies in the universe's infancy. Leisure remarked, "We have stumbled upon something completely unexpected that poses challenges to our scientific understanding. It calls into question the entire framework of early galaxy formation. According to current theories, the universe underwent a brief period of rapid expansion, followed by hundreds of millions of years of cooling, allowing gas to condense and collapse into the first stars and galaxies, known as the Dark Ages. The discovery of these massive galaxies so soon after the Big Bang suggests that the Dark Ages may have been a period of vibrant star formation, contrary to previous assumptions." Dr. Emma Chapman, an astronomer at the University of Nottingham not involved in the recent observations, emphasized the need for additional corroborating observations before outdated models can be discarded. Chapman stated, "Considering the pace at which the James Webb Space Telescope has been revolutionizing fields and overturning theories, it wouldn't surprise me if these findings were true." The team plans to obtain spectrum photos, which will provide more precise distance data and enable better estimates of mass. A spectrum analysis will serve as evidence for the existence of these galaxies. Science relies on revolutions, as has been witnessed throughout the history of physics and astronomy. Overturning prevailing beliefs is a recurring theme. For over a millennium, humans believed that Earth occupied the central position in the solar system. Nicholas Copernicus challenged this notion by proposing a heliocentric model, suggesting that we are simply one of the planets orbiting the Sun. The geocentric theory gradually crumbled in the face of mounting evidence from telescopic observations. Despite initial resistance, it became clear that the planets orbit the Sun due to gravity, as later explained by Isaac Newton. Newton's gravitational theories reigned for 2.5 centuries until Albert Einstein's general theory of relativity arrived in 1915, overthrowing Newton's laws. Einstein's groundbreaking perspective regarded gravity as a consequence of curved space rather than a mere force of attraction. He envisioned the universe as a seamless four-dimensional fabric called space-time, in which all objects are suspended. According to Einstein, the Earth's orbit is a result of our planet following the curvature created by massive objects like the Sun, which warp the surrounding space-time. This curved space-time concept has prevailed for over a century, resisting challenges to its dominance. However, its compatibility with quantum theory, the other powerful framework in physics, remains problematic. The quantum realm is renowned for its peculiarities, such as particles existing in multiple places simultaneously until observed. Prior to observation, we can only assign probabilities to likely outcomes. Erwin Schrödinger devised a classic method in the 1930s to demonstrate the absurdity of a particular notion. He envisioned a cat placed inside a sealed box with a hammer and a vial of poison. The hammer was connected to a device that measured a particle's quantum state. The outcome of this measurement would determine whether the hammer would break the vial, leading to the cat's death. However, according to quantum physics, until the measurement is made, the particle exists simultaneously in multiple states. Consequently, the cat is both alive and dead, and the vial is both broken and unbroken. This scenario challenges the idea of a uniform and continuous space-time fabric. Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, argues that a gravitational field cannot exist in two places simultaneously. However, quantum physics suggests that matter and energy can occupy multiple states and be present in different locations. Einstein proposed that matter and energy distort space-time. Hossenfelder poses the question, where is the gravitational field? Unfortunately, there is no definitive answer to this query. The concept of time and its nature also come into question. Time appears to flow continuously, pushing events forward like a river. It provides a framework for sequencing events and measuring durations. However, the debate arises as to whether these characteristics are inherent aspects of the physical universe or constructs of the human mind. Time may not be as it initially seems, a seamless, undivided whole, or an eternal stage for all events. Is time a tangible entity? According to Hugh Price, a philosophy professor at Cambridge University, the three fundamental characteristics of time, unique moments, passage or flow, and the block universe, are products of our mental processes, not the physical environment. The block universe, supported by Einstein's theory of relativity, portrays time as a component of four-dimensional space-time. Each event has a specific location in space-time, and all points are equally real, rendering the past, present, and future equally valid. Our brain's subjective perception shapes our understanding of time and causality. Max Tegmark, a physicist from the Massachusetts Institute of Technology, presents different ways to perceive reality. A three-dimensional place where events occur over time, a four-dimensional place where nothing changes, or a combination of both. If the block universe view holds true, change becomes illusory, and everything exists simultaneously, past, present, and future. Andreas Albrecht, a theoretical cosmologist at the University of California, Davis, asserts that time is an external parameter, an independent component in the equation of motion. Surprisingly, the concept of time diminishes when studying physics, only to regain significance in the realm of relativity. Some argue that there is no absolute time or space, as relativity suggests. Explaining time in the context of the cosmos requires understanding that time evolution arises from the interactions between specific parts of the universe and our chosen measure, the clock. So thanks for watching. Let us know your thoughts in the comments section.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.